Okay, this is 0654, Winter 19, paper 4.1, question 6. It's another physics one, this time about ultrasound. Okay. As soon as you think of ultrasound, what you need to be thinking of is the range of human hearing. Okay, range of human hearing is 20 hertz to 20,000 hertz. Why? We'll see in a second. Okay. Why is that important? Sorry. We'll see in a second. I'll just write it up here. Human hearing. Okay. We've got here a range of frequency emitted by a bat, and that is 2,000 to 110,000 hertz. Okay. State whether a bat emits any frequencies audible to a human and why. Well, the clear answer there is yes, they do. Okay, that's our statement. Okay, and then our explanation comes here. The range of human hearing is 20 hertz, to 20,000 hertz. Meaning that some of the frequencies given out by the bat are audible, i.e. it is possible to hear by the human ear. Okay, so if you like, we can hear the low frequencies that they give out, but those high frequencies we definitely can't hear. Alright, bat emits a pulse of ultrasound with a wavelength 9 times 10 to the minus 3. Speed of sound is 330 meters per second. We're asked for the formula to calculate our frequency. Alright, formula we're going to use here is the wave equation, V equal to F lambda. Hopefully we're getting this stuck into our heads just now. Okay, V equal to F lambda is very much the equation that we can use for any wave. Doesn't matter if it's water, light, sound, we can use this. That's our triangle, V F lambda. Well, if I cover up F, I've got V divided by lambda here, 330 divided by 9 times 10 to the minus 3. Okay. Now that's going to give you a stinker of a number, 3666666.6666666 recurring. Okay, call that 36,700 hertz. Okay, ultrasound is a wave. All right. Okay, ultrasound is a sound wave in particular, and that's a longitudinal wave, and it's made up of rarefactions and compressions. Okay, rarefactions and compressions. You're then asked to explain what the difference between them is. Well, compression is really the key point here. When we've got a compression, what's happening is those particles are moving close together. They're being compressed together. Rarefaction is the opposite of that, being pulled apart. Okay, and again, I've said this before, I use the idea of the accordion, an instrument you might see in the streets of Paris playing romantic songs, yeah? Okay, we press it in and out. That's compressing and rarefactions. Okay, so in a compression, particles are close together, and in a rarefaction, they're further apart. Another thing you could add there is to do with pressure. If we've got lots of particles close together, that is a high pressure point. If they're further apart, that is low pressure. All right. So you could, if you like, talk about ideas of high and low pressure here. Now, what is a compression? What is why are compressions important here? Well, compressions mark points of, say, high pressure, right? If we're drawing our wave, our sound wave, okay, one way I could depict this is like this, okay? That's the characteristic form of a wave. And what I could say is, well, I'm drawing pressure here. If I have a 0 point here, okay, this is high pressure, low pressure, high pressure, low pressure. Well, we've just said that a compression is a position of high pressure. If you notice there that the distance between these two things is a wavelength. Okay, so the wavelength is the distance between adjacent compressions. We've got one compression and the compression next door to it. The wavelength is the distance between it, and that's what we have to do. Notice that I have to use the word compression in my answer. Okay, so if I just use a general description of the wavelength, that's not going to be enough. Okay, notice this question coming up a couple of times. We're thinking about electromagnetic waves. Okay, for example, ultraviolet radiation. But actually, all of the radiation types, the radiation types that you should know here, gamma rays, visible light, microwaves, radio waves, they all travel 3 times 10 to the 8. That's what links them together. That's their family trait. Okay, and again, we've seen this kind of thing before. I think in a previous question we were asked to put invisible light. All right, in this case we're being asked to put in ultraviolet into the correct position. So that's my ultraviolet here, but just because I'm annoying, I decided to put in all of them as well, just to show how clever I am. Okay, I wouldn't suggest you do that in the exam, by the way. I'm just trying to give you as much information as I can. State where in the electromagnetic spectrum we have waves with high frequency, that's over this end. Okay, gamma rays have a lot of energy, they have high frequency. Radio waves, lower energy, lower frequency. Okay, remember what the frequency does is opposite to the wavelength. So here we have low frequency but high wavelength. Here we have high frequency but low wavelength. Okay, last bit, quite a long question. This one, we're being asked to calculate some time, but it takes a bat to fly. The equation we're going to use is d equal to v times t, specifically rearranging it to find the ratio of those two to find the time, and we're told it's speed. That's simply 200 divided by my speed, 22.2. Again, you get a 22.2 recurring here. Go for one decimal place there because that gives you 3 significant figures. Okay. Last one, kinetic energy of the bat, EK half mv squared. In this case, no rearranging to make. However, we do have to be careful with the units that we're given here. Anytime you want to use our kinetic energy formula, the mass must be in kilograms. We've been given it in grams. We need to convert that to 0.2 kilograms. We've got half of 0.2 times 9 squared, 8.1 joules.